Ever feel like understanding how an airplane flies is, well, this giant, complex puzzle?
It can definitely seem that way sometimes.
Right. So today, we're going to take a surprisingly focused look at some key pieces of that puzzle, the kind of details that hopefully can unlock a whole new level of understanding for you.
Mm,
We're not aiming to turn you into an engineer overnight, promise, but more about getting those satisfying aha moments without getting totally bogged down.
exactly. We're setting our sights on the fundamental aspects of aircraft engine technology and, some closely related concepts.
And our map for this journey, it's this comprehensive glossary, absolutely packed with definitions, engines, aerodynamics, systems, the whole lot.
Think of it as our cheat sheet.
Yeah, a cheat sheet to understanding the power behind flight.
And our mission really is to distill the core knowledge and insights packed into all this technical vocabulary.
Uh-huh.
We want to show how these terms, which might seem separate, are actually deeply interconnected. They form a complete picture of how these incredible machines generate thrust.
Make it make sense, basically.
Exactly. Make it make sense for you, the learner. Real understanding without feeling like you're, deciphering a textbook.
Okay, let's unpack this, starting with the very core where the power comes from. And let's begin with a foundational technology, reciprocating engines.
Good place to start.
Now, in simple terms,
Hmm.
what's the fundamental action happening inside one of these?
Well, at its heart, a reciprocating engine. It performs this really clever conversion.
Conversion.
Yeah, it takes a back and forth motion, reciprocating.
It's up and down.
And transforms it into rotary motion, spinning. That's what turns the propeller, ultimately.
Makes sense. So what are the essential components that make this happen? The parts we really need to know.
Okay, think of it like a chain reaction. It all starts inside the cylinder. That's the chamber, right, where the combustion happens.
Okay.
Inside there, you've got the piston. That's the movable plug. It compresses the fuel-air mixture.
Mm-hmm.
The cylinder also holds the valves controlling intake and exhaust, and the spark plug, which ignites everything.
Got it.
When that mixture ignites and expands, boom, it pushes the piston down, and that force gets transmitted through the connecting rod
To the
crankshaft.
Ah, the crankshaft.
Yeah.
That's the central piece that actually spins, isn't it? Taking that up and down and making it go round and round.
Precisely. The crankshaft has these offset parts called cheeks and an offset throw. That's where the connecting rod attaches.
And that offset is the key.
Absolutely key. It's how that linear push from the piston becomes rotation.
So this constant movement, it follows a very specific order, doesn't it? I remember hearing about a 4-stroke cycle. Why is that cycle so significant?
The 4-stroke cycle is, well, it's fundamental. It governs how these engines make power, and it's significant because it breaks the process into these really distinct phases, makes it efficient.
Okay, what are the phases?
4 distinct steps. First is intake. Fuel-air mixture gets drawn into the cylinder.
Right.
Then compression. Piston moves up, squeezes that mixture, build up potential energy. Then power the exciting bit. Spark plug ignites the mixture. The hot gases expand fast, forcing the piston down. That's your power.
Okay.
And finally, exhaust. Piston moves back up, pushes the used gases out, and the cycle repeats.
4 critical steps happening incredibly fast. Now, how do they maximize the power from that power stroke? I see a term here. Compression ratio. What's that telling us?
Compression ratio. Yeah, that's crucial for efficiency. It's basically the ratio of the volume inside the cylinder when the piston's at the bottom
Okay.
compared to the volume when it's right at the top. How much it squeezes the mixture.
And a higher ratio means?
Generally, a higher ratio means more potential energy packed into that mixture, so you get a more powerful expansion, more power output.
Yeah.
Designers are always playing with this for efficiency.
Makes perfect sense. Squeezing it tighter gets a bigger bang. Now, all that controlled explosion must generate a ton of heat. How do these engines stop themselves from melting?
Yeah, cooling is absolutely vital. You've got air cooling, which is pretty direct. The cylinders have fins.
So like on a motorbike engine.
Exactly like that. Air flows over the fins as the plane moves, carrying heat away.
Okay. And the other type?
Liquid cooling. That uses a coolant, usually a water glycol mix, circulating through channels in the engine.
It's like a car radiator system.
Very similar. The hot liquid goes to a radiator, air flows through it, cools the liquid down, and it circulates back.
Are there other less common methods mentioned?
There are. You might see steam cooling, which uses the boiling point of the coolant to transfer heat very efficiently, and something called an augmenter tube, which uses exhaust gases to help suck more cooling air through. A bit more niche, those ones.
Okay, so managing heat is crucial. What about keeping everything moving smoothly, reducing friction? That's lubrication, right? I see wet sump and dry sump engine. What's the difference?
Exactly. Lubrication is key. In a wet sump engine, the oil supply is right there in the engine, usually in a pan at the bottom, like its own little oil reservoir.
Got it. And dry sump?
A dry sump engine stores its oil in a separate external tank.
Why do that?
It generally allows for more consistent oil pressure, especially if the aircraft is maneuvering aggressively. You often find them in higher performance planes.
Okay. What about oil dilution? Sounds odd.
It's a technique for very cold weather. You temporarily mix a tiny bit of fuel with the oil to make it less thick, less viscous. Helps with starting when it's freezing.
Ah, clever. And this AD oil?
AD oil stands for ashless dispersant. It's a type of oil designed to hold onto combustion byproducts and tiny contaminants, keep them suspended so they don't build up as sludge inside the engine.
Right, keeping things clean inside. Okay, so we've got air and fuel in, compressed it, ignited it for power, got rid of the waste, kept it cool, kept it oiled. Now, that critical spark, magneto and spark plug, how does that ignition actually happen?
Okay, the ignition system. This kicks off the power stroke. A magneto is basically a self-contained generator. It's driven by the engine itself.
So it doesn't need the plane's battery?
Nope. It makes its own high-voltage electricity. That electricity goes to the spark plug.
And the spark plug?
The spark plug delivers that high-voltage zap across a small gap inside the cylinder, igniting the compressed fuel-air mix.
And I see dual ignition mentioned a lot.
Very common. Means you have two separate magnetos and two spark plugs for each cylinder.
Redundancy.
Huge safety factor, yes. If one system fails, the other keeps the engine running. Plus, igniting the mixture in two places at once gives a better, more complete burn, more efficient.
Are there other ignition details, like special plugs or systems?
Sure. You've got things like all-weather spark plugs for high-altitude reliability, maybe a shower of sparks ignition system, which gives a really strong spark for starting, especially when the engine's turning slowly. Even the internal timing of the magneto, the E-gap angle, is critical for getting the spark just right.
Wow, a lot goes into just getting that spark. Amazing, a mechanical thing like a magneto does that. Okay, last piece for reciprocating engines, controlling that crucial air and fuel mix. Air-fuel mixture ratio. What's the key thing here?
The air-fuel mixture ratio is simply the proportion of air to fuel by weight going into the cylinders. Getting this ratio right is absolutely critical.
Critical for what?
For efficient combustion, for engine health, preventing damage. You might have an automatic mixture control, AMC system, that adjusts this automatically as you climb or descend because air density changes.
And you can have lean or rich mixtures.
Right. A lean mixture has more air, less fuel. A rich mixture has more fuel, less air. Go too lean, and you risk really bad stuff, like detonation.
Which is?
An uncontrolled, violent explosion in the cylinder. Very damaging. Or pre-ignition, where the mix lights off before the spark plug fires. Also very bad.
Yikes. Okay, definitely want the right mixture, right? That gives us a really solid foundation in reciprocating engines. Now, let's shift gears completely. A fundamentally different way to get power. Gas turbine engines.
Okay, turbines. Big difference.
What is the core distinction compared to the reciprocating ones we just talked about?
The biggest thing is the operating cycle. Reciprocating engines are cyclical, right? Stop-start strokes. Gas turbine engines work on a continuous flow principle. It's called the Brayton cycle.
Continuous flow.
Meaning air is constantly moving through the engine. It's undergoing all the stages, compression, combustion, expansion simultaneously, just in different sections of the engine rather than one after another in the same cylinder.
Okay, continuous flow. So what are the key sections that make this constant process work?
You've got these core parts. First, the compressor right at the front. Sucks air in, squeezes it, raises the pressure dramatically.
Are there different types of compressors?
Yep, two main ones. Axial flow compressors use rows of spinning blades and stationary vanes to gradually increase pressure along the engine's axis. Think multiple stages. Centrifugal compressors use a spinning impeller to fling the air outwards, increasing pressure that way. More common in smaller turbines or older designs.
Okay, compressed air goes where next?
Into the diffuser. It's a widening duct. It slows the really fast air down a bit, which actually increases the pressure even more before it hits the combustor.
The combustor. That's where the fire happens.
That's the hot section. Fuel is continuously straight in and ignited. Massive increase in temperature and gas volume.
And those hot gases.
They blast through the turbine. This makes the turbine spin incredibly fast. The turbine's job is partly to drive the compressor at the front.
Ah, so it powers itself in a way.
Exactly. And then the remaining hot, high-velocity gas shoots out the back through the exhaust nozzle. That's what produces the thrust in many turbine types.
So a continuous loop. Intake, compression, combustion, expansion through the turbine, and exhaust. All happening at once. Now, I know there are different kinds of turbine engines. Can you walk us through the main ones?
Sure. The sort of baseline type is the turbojet engine. It gets most of its thrust directly from that high-speed exhaust jet, pure jet power.
Okay, what else?
Then you have the turbofan engine, which you hear called a bypass engine a lot. This is what most modern airliners use.
How does that work?
There's a big fan at the very front, driven by the turbine. It moves a huge amount of air, but a lot of that air actually goes around the core engine. It bypasses it.
And that bypassed air does what?
It also produces thrust, just like a big propeller, essentially. And it makes the engine much quieter and way more fuel efficient, especially at subsonic speeds.
Ah, hence the bypass ratio term.
Exactly. That ratio tells you how much air goes around the core compared to how much goes through it. High bypass ratio engines are the really efficient ones on airliners. Low bypass ratio engines might be on faster jets, where pure jet thrust is more important.
Okay. What about turboprops?
A turboprop engine uses the turbine, but its main job isn't producing jet thrust. It's driving a traditional propeller.
How does it slow down the turbine speed for a propeller?
Through a set of reduction gears. The turbine spins incredibly fast, way too fast for a propeller, so the gearbox slows that rotation down to an efficient speed.
Got it. And finally, turboshaft.
Turboshaft engines are similar, but instead of a propeller, they deliver power through a shaft. The helicopters, the engine drives the main rotor shaft, or they can power generators, things like that.
So turbojets for speed, turbofans for efficiency, turboprops for propellers, turboshafts for rotary power. Makes sense. How do engineers keep track of how well these powerful engines are running?
Two really key parameters they monitor are engine pressure ratio, EPR.
Which measures?
It's the ratio of the pressure leaving the turbine to the pressure entering the compressor. Basically, how much the engine is increasing the air pressure overall. A good indicator of thrust.
Okay. And the other?
Exhaust gas temperature, EGT. That's the temperature of the gases coming out of the turbine. Tells you about the thermal stress inside the engine, how hot things are running. Very important limit.
Now, with all that air being compressed at high speed, I imagine things can go wrong. Compressor stall and compressor surge sound? Unpleasant.
Oh, definitely unpleasant. You want to avoid those. Compressor stall happens when the airflow over the compressor blades gets disrupted. They stop flying properly, basically.
Like a wing stalling.
Exactly. Yeah. Analogous. And if it gets bad enough, it can lead to compressor surge. That's a complete breakdown of airflow. Air can actually flow backwards through the compressor momentarily. Lots of noise, loss of thrust, potential damage.
How do they prevent that?
Complex design, careful control systems. Some engines have blow-in doors, little auxiliary air inlets that can open automatically to give the compressor more air if needed, helping prevent stalls in certain conditions.
All this heat and pressure must be incredibly tough on the materials inside. I see creep mentioned. What's that?
Creep is a huge challenge. It's the tendency of metals to slowly, permanently deform over time when they're under stress at very high temperatures.
Like stretching?
Like stretching, yeah, but very slow and permanent. Given the conditions in the turbine section, materials have to be incredibly resistant to creep. That's why they use exotic stuff like Inconel, these nickel-chromium superalloys.
Makes sense. And lubrication. Similar to reciprocating, or are there unique bits for turbines?
Similar need, but the systems are often more complex because of the high speeds and temperatures. They often use things like an air oil separator.
You what?
To get air bubbles out of the oil. Air gets whipped in at high speeds, causes foaming, which is bad for lubrication. A deaerator does a similar job.
Any other lubrication terms?
You might hear about cold tank versus hot tank lubricating systems, depending on where the oil cooler sits in the circuit. And there's usually a last chance oil filter right before critical bearings, just as a final safety net.
How do you even start these massive engines?
Often with an air impingement starter. High-pressure air is blasted onto the turbine blades to get them spinning. Some smaller ones use a starter generator. One unit acts as a starter motor, then switches to being a generator once the engine's running.
Okay, wow. We've covered the power generation, reciprocating, and turbine. Let's zoom out a bit. Some fundamental concepts about how engines interact with air seem crucial for both airflow and pressure.
Absolutely fundamental stuff, yeah. You start with ambient air pressure, just the pressure of the air around the aircraft.
Okay.
Then you have absolute pressure, measured from a perfect vacuum, zero pressure, and gauge pressure, which is measured relative to whatever the current atmospheric pressure is.
Like tire pressure.
Exactly, that's gauge pressure. And differential pressure, the me, is just the difference between pressures at two different points. useful for measuring flow or pressure drops.
Got it. Different ways to measure pressure. Now, Bernoulli's principle always seemed a bit magic. Faster air, lower pressure. How's that relevant here?
It's less magic, more physics. But yeah, Bernoulli's principle says that for a fluid like air, as its speed goes up, its stomach pressure goes down. It's a core aerodynamic principle.
And how do engines use it?
A classic example is the venturi in a carburetor. The tube narrows, air speeds up through the narrow bit, pressure drops.
And that sucks fuel in.
Precisely. That pressure drop draws fuel from the float bowl into the airflow. But that same principle, faster air, lower pressure, is also fundamental to how wings generate lift. It connects engine tech and aerodynamics.
That's a cool connection. What about ram air and ram pressure?
As the aircraft flies forward, air is basically forced or rammed into the engine intake. That's ram air. The kinetic energy of that moving air gets converted into pressure inside the inlet. That's ram pressure. It actually helps the engine by pre-compressing the air a bit, especially at higher speeds.
Is there a downside?
Well, scooping up that air creates ram drag, a resistance force. There's also a term ram recovery speed, which is basically the speed where the ram effect perfectly compensates for pressure losses due to speed.
Okay, using the plane's motion to help the engine. Clever. Now let's talk control and monitoring. Modern engines seem incredibly smart.
They really are. The big one is FAA-DTC, Full Authority Digital Electronic Control.
Sounds important.
It is. It's basically a dedicated computer brain for the engine. Manages almost everything: fuel flow, ignition, even adjusting parts inside the compressor for efficiency. It optimizes performance and safety constantly.
Was there something before FADEC?
Yeah, earlier systems were often called EEC, Electronic Engine Control. Less comprehensive, maybe. FADEC is kind of the gold standard now. Total digital management.
What's ACC? Active Clearance Control.
Yeah. That's super precise. It manages the tiny gaps between the tips of the spinning blades compressor and turbine and the engine casing around them.
Why control that gap?
Keeping that gap as small as possible without parts actually touching massively improves efficiency. Less air leaks past the blade tips. ACC actively adjusts it based on conditions.
Wow. And the ADC, Air Data Computer.
That's crucial too. It senses things like air pressure, temperature, airspeed from outside the aircraft. It feeds that data to FADC, flight instruments, other systems. Really vital information.
How does the crew see all this? I see ICAS.
ICAS Engine Indicating and Crew Alerting System. It's the modern display in the cockpit. Shows all the key engine numbers, EPR, EGT, RPM, fuel flow, oil pressure, everything on screens.
All in one place.
Usually, yeah. Integrated display. And it gives alerts if anything goes wrong. Any exceedance conditions, meaning a parameter went outside its safe limits, much clearer than rows of old gauges or an old-style annunciator panel with just warning lights.
Remarkable level of automation and information. Now, safety. Obviously number one in aviation. What are some key terms related to keeping these engines safe and reliable?
Top of the list maybe is the Airworthiness Directive, or AD.
What is that exactly?
It's a legally mandatory order from the Aviation Authority, like the FAA. If they find an unsafe condition on a type of aircraft, engine, propeller, whatever, they issue an AD requiring specific inspections or modifications. You have to comply.
Okay, legally required fixes. What about regular checks?
You have required periodic checks like the annual inspection, or for aircraft used commercially, the 100-hour inspections, keeping things maintained on schedule.
How do they inspect inside an engine without taking it apart?
Using a borescope. It's like a tiny camera on a flexible or rigid tube. Modern ones use fiber optics to get light in and the image out. They can even capture a digitized image to look at closely later.
What about finding cracks you can't see?
For metal parts, especially steel, magnetic particle inspection is common. You magnetize the part.
How?
Using techniques like circular magnetism or longitudinal magnetism, then you apply fine magnetic particles like iron filings. If there's a surface or near-surface crack, it disrupts the magnetic field, and the particles gather there, making the crack visible.
Clever. Are there different ways to do that?
Yeah, continuous magnetic particle inspection, where you apply particles while the magnetizing current is on, or residual magnetic particle inspection using the magnetism left in the part after the current is off. Depends on the material and type of flaw.
What's oil analysis, or SOAP?
SOB stands for Spectrometric Oil Analysis Program. Basically, you take regular samples of the engine oil and send it to a lab.
And they look for
tiny microscopic metal particles. The type and amount of metal tells you if specific parts inside the engine, bearings, gears, cylinders, are wearing abnormally. It's like a blood test for the engine, giving early warnings.
That's proactive. What about fire safety? Fire sleeve.
A fire sleeve is just a protective covering, usually silicone-coated fiberglass, put around fuel or oil lines in hot areas like the engine compartment, helps resist fire for a short time if needed.
And FOD. Sounds like a problem.
Big problem. FOD means foreign object damage. Anything getting sucked into an engine that shouldn't be there. Tools, runway debris, birds can cause major damage, especially to turbine engines. Airports work hard to prevent FOD. Sometimes you see devices like a vortex dissipator used on the ground to blow air and reduce the chance of sucking things up.
Right, keep the insides clear. It's amazing the layers of safety and inspection. Okay, one last area. For engines driving propellers reciprocating or turboprop, there's the whole world of the propeller itself. Let's touch on some propeller principles.
Okay, the propeller. It's essentially a set of rotating wings or airfoils. Its job is to convert the engine's rotation into forward thrust.
What are the key parts of a propeller?
You have the individual blade, the central hub that attaches it all to the engine shaft. Each blade has a curved side, the back, and a flatter side, the face. Like a wing, it has a leading edge and a trailing edge, and the imaginary line between them is the chord line.
And angles are important here, right? Pitch angle and angle of attack.
Absolutely critical. The pitch angle, or blade angle, is the angle between that chord line and the plane the propeller is spinning in. How flat or coarse the blade is set.
Okay. And angle of attack.
The angle of attack is the angle between the chord line and the actual airflow hitting the blade, the relative wind. This is what determines how much lift, or in this case thrust, the blade produces. Just like a wing.
Are there forces trying to twist the blade?
Yes, two main ones competing. Aerodynamic twisting force, ATF, comes from the air pressure distribution and tends to twist the blade to a higher pitch. Centrifugal twisting force, CTF, comes from the rotation and tries to twist the blade flatter to a lower pitch. Designers have to balance these.
And sometimes pilots need to feather a propeller. What's that for?
Feathering is usually for an engine failure on a multi-engine plane. You rotate the blades so they're edge onto the airflow, a very high pitch angle, almost 90 degrees.
Why?
It stops the dead propeller from windmilling and creating huge amounts of drag. Makes the plane much easier to control with the remaining engine.
I see geometric pitch versus effective pitch. Difference.
Geometric pitch is like the theoretical distance the prop would move forward in one turn if it were screwing through a solid. Effective pitch is how far it actually moves forward through the air.
And the difference is?
That difference is called slip. It represents the fact that air isn't solid, so the propeller isn't 100% efficient at converting rotation to forward motion.
How do constant speed propellers work? I see governor.
Right, many planes have constant speed props. The governor is the brain. It's a clever device, usually using oil pressure and flyweights, that automatically changes the blade pitch angle to keep the engine RPM constant, even if you change power settings or airspeed.
How does it know?
It senses the engine speed. If it's in an on-speed condition, it does nothing. If the engine speeds up over speed condition, the governor increases blade pitch, takes a bigger bite of air, to slow it down. If it slows down, under speed condition, it decreases pitch to let the engine speed back up.
Clever.
Yeah.
What's asymmetrical loading?
That happens especially at high angles of attack or low airspeeds, or with engine failures. The descending propeller blade on one side takes a bigger bite of air than the ascending blade on the other side, creates uneven thrust across the propeller disc, which can make the aircraft yaw. Pilots have to counteract it.
And making sure the prop itself is balanced.
Mandrel. Yeah, balancing is critical for smooth operation. A mandrel is a precision ground steel bar that you mount the propeller assembly on to check its static balance very accurately.
Wow. This has been an incredibly insightful deep dive. Looking back at all those terms from the glossary, the way they all connect really paints a picture, doesn't it? The sheer ingenuity behind making flight work.
It really does. And what strikes me is how, fundamental physics principles like Bernoulli's get applied in such sophisticated ways across the board. Engines, wings, it's all connected. And thinking about the extreme conditions, heat, pressure, speed, the advances in materials, the control systems like FADC, it's just remarkable engineering, really shows the evolution.
Absolutely. And thinking about how these different approaches, the sort of stop-start power of reciprocating engines versus the continuous flow of turbines, are just different solutions to the same fundamental problem. Creating thrust makes you wonder what's next, doesn't it? What future innovations are coming?
And that precision you mentioned earlier, like active clearance control, adjusting blade tips on the fly, it just speaks volumes about the level of optimization and detailed engineering in modern aviation. It's not brute force, it's incredibly refined.
Well, hopefully this deep dive has given you, our listener, a clearer, more connected picture of some of this amazing technology. What aspect of aviation has really sparked your curiosity today? We're always ready for another deep dive.